welcome to my talk. My name is Xin Ning, and I'm a PhD student at Rensselaer Polytechnic Institute in Material Science and Engineering Department. So today, I would like to introduce about nanoparticle assembly through polyethylene crystallization. So first, I would like to discuss about why polyethylene, why semi-crystalline polymer nanocomposite. There is a report at 2015. It shows that polyolefins represent about 55% of global thermoplastic demand. However, the application is limited due to relatively low mechanical properties or dielectric properties. So people were thinking that maybe we can incorporate nanoparticles to enhance or optimize those macro properties. And here are two examples that by optimizing the permittivity, the mechanical properties, or the electro-optical properties, and they can be applied as cables or displays. However, there is a problem that is due to the van der Waals attractive forces between the nanoparticle failures. The nanoparticles are preferred to form agglomerations due to the polymer matrix in the polymer matrices. So how to control the nanoparticle dispersion in the polymer matrices is a very important problem. So we were thinking that to figure out the dispersion, we can do the surface modification by grafting polymer or organic ligands on the surface of nanoparticles. And then inspired by this nature structure, nuclear structures, and people find that this kind of layered structure has significantly high mechanical properties. And we were thinking that whether we can, on the basis of control the nanoparticle dispersion, whether we can further tune in the organization of nanoparticles and form such kind of string-like structures. And the idea is that we can control the polymer crystallization rate and then tune in the diffusivity of the nanoparticles. If after doing the surface modification of nanoparticles, and the surface energy is tuned, and nanoparticle can well disperse into the polymer matrix. And if we quench the nanoparticle from the melt state to the room temperature, and the nanoparticle will not have enough time to move around because of the crystallization rate is very fast, and they will engulf into the polymer matrix and stay as well they are. However, if we very slow control the crystallization rate, and the nanoparticle will be preferred to push into the solidification front due to in order to release the thermal energy, heat energy. And then if we approach a very slowly crystallization rate, the nanoparticle can be aligned between the lamina interface, the crystalline regions. And if we further decrease in the crystallization rate, the nanoparticles can be pushed between the spherulite boundaries like this. And so we grafted carbon-18 on the nanoparticles to change and optimize the mobilities of the nanoparticles in the polymer matrix. And here is a phase diagram that we developed by varying the grafting density and grafting chainness and versus the ratio of grafting chainness over the polymer matrix chainness. And by varying those kind of parameters, and we can control the dispersion state from well dispersed to phase separated or the string-like structures. And we choose two molecular weight matrices as examples. One is low molecular weight, and one is high molecular weight matrices. And by tuning the molecular weight, we can see we can either achieve well-dispersed morphology or phase-separated morphology. And here is an example that 4K molecular weight matrix, and we can achieve very well-dispersed, individually dispersed nanoparticles. And this is pretty stable, and after annealed at high temperature, above the melting temperature, and the dispersion can stay. It's very stable. And then we control the crystallization rate to tune the diffusivity of the nanoparticles. We can see just varying temperature, isothermal crystallization temperature from 103.5 degrees C to 105 degrees C, only 1.5 degrees C differences, and the half crystallization time changed from 3 minutes to 40 minutes. And only this 1.5 degrees difference, we can see a huge different morphology difference. And this is the low temperature, low temperature, we barely see the alignment of the nanoparticle assembly. But for the 105 isothermal crystallization temperature, we achieve very beautiful organized nanoparticle alignment. And this is the lower mag. We can see larger area of different orientation of the alignment. And this is an AFM image. We can see by telling the different height, and we can analyze what is the difference between the amorphous region and the semicrystalline region. And we can see the yellow part are the amorphous region, and nanoparticles are aligned into the amorphous region between the semicrystalline lamellar structure. And we further develop and characterize the despacing of the bulk materials and see what is the despacing between those nanoparticle alignments. And by analyzing the order of the structure, and we can see that there is around 33 nanometer despacing, which is relative to the despacing between the alignment plus the size of the nanoparticle, which matches our AFM results and TEM results as well. However, when we tune our idea into an engineered system, and because of the poor miscibility of the nanoparticle in the polymer matrix, we saw such kind of phase separation morphology. And due to the poor miscibility, those morphology, even though we achieve those kind of alignment, but the despacing between those alignment is way much larger than the lamellar despacing. And then we further analyze with the small angle X-ray and characterize how the order of the what's the ordering corresponding to the crystallization temperature, and it turns out that the ordering of the nanoparticles decreases with the decreasing isothermal crystallization temperature. So how the mechanical properties, macro properties can be affected by those kind of dispersion. And according to the literature, it shows that by increasing the crystallinity, the mechanical properties like storage moduli will be increased. And so it will become more complicated because by doing the isothermal crystallization, the crystallinity will be increased. But by comparing the composite one versus the neat sample, we can see still around 10 to 20% increasement. That is mainly because of the alignment of the nanoparticles. And this is the dielectric properties of the composite sample versus the neat sample. And the blue sample, the dark black blue sample is the isothermal crystallized sample with well-organized nanoparticle alignment. We can see the permittivity is increased significantly compared with the other sample. And one interesting thing which is opposite to the mechanical property is that the crystallinity, the permittivity increased with decreasing permittivity. So the isothermal crystallized sample has the highest crystallinity, but it also shows the very high permittivity. This is mainly because of the alignment of the nanoparticle instead of the crystallinity. And we can see the high molecular weight sample, it shows different trend, even though it has alignment. So the alignment sample, which is the dark red, it is relatively lower permittivity compared with the quench sample. That's mainly because the poor miscibility of the nanoparticles, and which results in a very low order of the assembly, nanoparticle assembly. So by doing the surface modification of the nanoparticles as well as control the isothermal crystallization temperature, we control and tune the diffusivity of the nanoparticles into the polymer matrix, and thus we can control the organization of the nanoparticle assembly. And this is a very normal method to control and tune nanoparticle organization and to optimize the mechanical properties as well as dielectric properties as well. So this is a picture of our group and Dr. Linda Shadler's group. And most of students are graduates, and those are our collaborators in Columbia University, South Carolina University, and the University of Vermont. Yeah, thank you. Please feel free to ask any questions.
Open for questions. I have a quick question.
Yeah, sure.
What do you think happened just by changing a couple degrees C, then this crystallization time dramatically reduced?
So the reason we changed the isothermal crystallization is that we changed the supercooling, the difference from crystallization temperature to the melting temperature. So the larger supercooling temperature difference will cause the faster crystallization rate. And as we introduced before, if the crystallization rate is very fast, the nanoparticle will not have enough time to move around to get organized. However, if we can very slowly control the crystallization rate, the nanoparticle will be pushed into the solidification front and get organized between this laminar structure. Yeah, so that's the key point, how we control the crystallization temperature to control the crystallization rate, and thus control the diffusivity of the nanoparticle.
So in general, the melting point is low, right?
In general, so it very depends on the molecular weight of the polymer matrix. And for the 4K sample, and the time window, the temperature window is very small, at around 1.5 degrees C. But for the high molecular weight sample, and we can control because it has longer time to for the polymer chain entanglement. So that's the time window and temperature window can be larger.
Have you considered using nanowires instead of nanoparticles? And also
Well,
specifically nanowires that do not interact strongly with your matrix. And
well,
for like say thermal cycling around your, the critical phase changing temperature.
Yeah, it is very interesting question, and I believe there are tons of researchers, our groups analyze, develop the nanowire in the polymer matrices. And one interesting thing is that nanowire has a different ratio. The ratio, the longitude and the latitude ratio is different. So that probably can affect the properties a lot as well. And also another thing is that the surface modification of the nanotube, it might be also a problem to need to figure out. For the reason we choose nanosphere is that there are many unknown things and possibilities we can control. Like we can control the graphene densities, graphene chain lengths, and we can train the different morphologies as well. Yeah.
If no more questions, let's thank you.
Thank you.